Okay, the purpose of this video is to get you started doing inference with means. So we did lots of inference with proportions. We did one proportion and two proportion, intervals, and tests. The intervals are those confidence intervals. So we need to do all of them for means as well. So we're going to start by doing a confidence interval for a single mean, and then we'll move on and do a test for a single mean, and then an interval for two means, and this for the difference of means, I should say, and then a test for the difference of means. All right, so we're going to go through the same kind of tour that we did with proportions. Now, there's a bunch of similarities, but there are some distinct differences, and the differences are a bit technical, so I do my best to try to get across what's the same and what's different. All right, so this recall I started with is just to really get a handle on the notation and to know exactly what it is we're talking about. So what we're going to be doing with inference with means is we're basically not going to know the population mean or the population standard deviation. Those things, when we do inference, are unknown, and we're trying to use a sample to estimate them as best we can. So the symbols for a single member of the population, remember, if we have a population and we want to know what's the average, say we're talking about maybe people's heights, what's the average height for a single person and what's the standard deviation from that, the population mean is symbolized by this Greek letter mu, and the population standard deviation is represented by the Greek letter sigma. So in a previous example, I think I had put roughly that in the population of American males, the average height is about 5'9". So a given person isn't necessarily 5'9", but on average, if you average the entire population, an average guy is a little more than, I think it was 5'9.1" or something. Let's just say 5'9". It was 5'9", but then there would be a spread. Not all men are 5'9", so you'd find that the heights of men are actually normally distributed. Now, the original population doesn't have to be normally distributed to do any of this, but in the case of heights, they happen to actually be normally distributed. So what you'd find is, using the standard deviation, whatever that was, I think it was maybe 2 or 3 inches, as you got farther away from the mean, you'd be less likely to find anybody out there. So basically, the mu and the sigma are representative of a single member of the population. What would be the average for a single member, and then how much do we expect a single member to deviate from that average? Now, in that last video, we talked about the sampling distribution for a sample of a certain size. So this says the sampling distribution information for a group of size n from the given population. So if we take a certain sample of a particular size, let's just go with the heights of American males like we did. Say we took 100 American males at random. They would have their own average. That average would be called X bar. Now, X bar is not going to necessarily be what mu is, but X bar should be close, and it would be rare to get X bar to be far away. Now, it's possible, but the farther you get from mu, the less likely you are to get an X bar like that. So if I took a sample size of 100 men, they might come out as 5'9.5", or maybe they come out as 5'8 3/4. Now, it's possible they'd come out maybe at 5'11", but 5'11" is getting farther from the 5'9" that their average is. So the farther you are, the harder it is for you to be that value, especially as the sample size goes up. So that's what this measures. If I take a sample of a particular size, I'll get a certain average. How far can that average sort of spread from this value? It's measured by this. So basically, when we did the example of the 100 men and then came to the conclusion in that last video that they were probably lying, it was because the chance of getting their X bar to be that far from the mean based on the standard deviation we calculated was basically really, really, really hard to do. It would be very, very, very rare. So either an extremely rare thing happened or the men were lying. So we kind of went with it's probably the men are lying, though we weren't 100% sure. So realize that when you take a certain sample size, like you grab 100 people out of the population, they have their own mean, which is called X bar. And then how much that thing can spread is based on the sample or the single member standard deviation. But with a bigger group, that spread goes down. It's harder for a larger group to have to basically deviate than it is for a single person. So the calculation is based off of the standard deviation for a single person, but you have to divide by the square root of the group size that you have. All right. So if I take a sample size of 100 men, square root of 100 is going to be down here, and it's going to cut the standard deviation by 10, because that's the square root of 100. The bigger the sample, the less it can deviate. So I had mentioned that in like the classroom example. A single person's grades can deviate a decent amount, but the entire class average doesn't deviate as much because more people are in there, and it's harder for the entire group to deviate from the mean than for a single person. The bigger the group, the harder it is to deviate. So this thing will have a tougher time getting away from the population mean. Now, I don't think I talked about this in the last video, but this is going to come up now. When you take the sample itself, I had mentioned already that, well, the sample has its own mean. Now, the sample also has its own standard deviation. The population has a standard deviation, but since you're not grabbing everybody, the standard deviation itself won't match the population. Now, the difference between these is that this tells me how much the mean's able to get away from here. So this is a measurement of, given the population mean, how much the sample mean is able to basically vary given your sample size. That's based on this number. Now, the sample itself has its own standard deviation. The trouble we're going to run into is that this number and this number don't really have to have any connection. You can get a sample that has kind of any standard deviation. It can be unique to the sample itself, and it might match this, but it might not. So the problem here is that the sample itself has its own standard deviation, different from the population standard deviation, and also different from how far the mean can escape from here. So these are three different measurements. They each measure a different thing. So hopefully you can keep a grasp on that, because if you can, then it makes it easier to do the problems, because there's a lot of different things running around. There's different averages and different standard deviations. So just to recap one last time, the population has a mean and the sample has a mean. The sample has its own standard deviation, and then the ability for the sample mean to stray from the population mean is measured by this. This is basically the sample size standard deviation. It's a measurement of how much the mean can vary. It's not a measurement of the variance or how much the data itself varies. So this one is for the data itself. This one is for how much the mean will move based on the population mean. So I feel like I've said that 9 times. Hopefully that makes some kind of sense. All right. So with this in mind, we will look at goal 10, which is being able to make a confidence interval for means using what's called a one sample t interval. Now, before when we did this, we called it a one proportion z interval. Since we're not doing proportions, we're doing means. Sample stands for sample mean. So it's a one sample mean, And then this thing is a little weird because the Z stood for Z-score from a normal curve. There's a problem where we can't quite use a normal curve. We have to use something that's close. There's another distribution called a t-distribution, which I'll have to talk about. So there's a lot going on in this, but if you can get a grasp of this t-interval stuff, that will also help for all the subsequent lessons. All right, so we're going to make a confidence interval for means instead of proportions, and the confidence interval for one mean that we're going to talk about is referred to as a one-sample t-interval. All right, so always helps to have a good example, so hopefully this will get the point across. In class, I would have given this for people to calculate, and then we would have seen how this connects to doing a confidence interval. Basically, well, I'll just do it for you, unless you want to stop and see if you can calculate these. Basically, the warm-up says that we're outside of the school. I probably would have just said, pretend it's the Reynolds Road outside the high school. So the following speeds are recorded by cars randomly, picked systematically on a road going by a school. We'll just say it's, like I said, Reynolds Road going by the high school. There's a speed of 30 miles per hour out there at the end of the school day. So the speed limit's 30, but clearly not everyone's going to go 30. You'll get some people going a little slower, but then you'll get some people who are going faster. So they took a random sample of 23 of these cars, and this is what they found their speeds to be. So it asked to find the mean standard deviation for the data. You could put this in the calculator in a list and do one variable stat, and one variable stat, if you gave it the right list, would come up with the mean standard deviation. So the mean comes out to be 31.04. So the average speed of these cars is 31.04 miles an hour. The standard deviation comes out as 4.25, both are rounded to the nearest hundredth. So we expect, on average, the car is going 31.04, so the average car is speeding, but it has a spread of 4.25. So it's not too uncommon for a car to go about 4, maybe even 8 miles an hour above the speed limit. Same thing on the other side below. So here's where the confidence interval comes in. A group of parents are concerned that people are exceeding the speed limit. In fact, we have evidence that that's the case. The example that has the average 31.04, so on average they're speeding. But here's the issue. Even though the mean of the sample is above 30, we took a sample. We didn't measure every single car. We didn't do a census. We just took a sample. So it's possible through random variation that we just happened to get a sample that was a little above. It could be the population of cars is actually going 29, but we just got kind of an unlucky sample, and that sample came out as 31.04. So our trouble is, even though we do have evidence of the sample speeding, is this evidence of the population in general speeding? So the questions are, can we figure out what the real mean is? Well, we can't know for sure what the real mean is for everybody unless we did a census. However, can we construct an interval for it? Well, that's what this entire lesson's about. So the answer is yes. We can come up with a confidence interval for what we think the actual mean of all the cars are that go by the school. And we want to then make an interpretation. Once we get this interval, does it suggest that this sample is indicative of the greater population speeding? Does this suggest the real mean speed is significantly different from the posted speed? All right, so the posted speed's 30. We have them at 31.04. Is it possible this 31 is consistent with the fact the greater population is doing the speed limit? Or is this sample of speeding an example that the group is actually speeding? All right? So that's what we want to answer. So from that last lesson, the distribution of sample means is normal for significantly large samples, regardless of the data distribution. So we took a sample mean. It was 31.04 miles per hour. If we took other samples, we would get other values. But remember, the distribution of means should be normally distributed. So as we took more and more X bars or more samples and found their averages, they would cluster around the population average. And values that were far away from the population average would be rare to get. That central limit theorem tells us that the mean of the samples is the population mean. So if I took lots and lots of samples of that size 23, most of them would come out close to the real value. In fact, if we took lots of them and then averaged them, they should be very close, if not right on the population mean. And that's according to that central limit theorem from the last unit. It also gives us the standard deviation for the sample means. So most of our samples will cluster around the population mean, and we can have a measurement for how far they're able to deviate from that. So remember that standard deviation, which I had gone over in the beginning, for this distribution of the sample means, how far can those X bars get away from mu? It's measured by sigma over the square root of n. So in our case, our n's 23, so we would go over the square root of 23. With this info, we can make confidence intervals and do hypothesis testing in a similar fashion to the proportions. Meaning, basically, with a mean and standard deviation, we can make the sampling distribution, and then we can use that to make a confidence interval or test a mean against a hypothesis. Of course, this is why we go over the second. There is a problem with this. The major problem we're going to run into is in the problem, we don't have sigma. We only have a sample, and we don't have the population mean. That's what we're trying to sort of infer, and we don't have the population standard deviation either. And there's actually no way to get it. So when we go to do the standard deviation, since we don't have that sigma, we have to go with an estimate. We have to do the standard error. We did standard error with proportions. We ran into the same problem with proportions where we didn't have the population proportion. But the difference is the standard error was related to the proportion. So once we had some estimated proportion, we could come up with that standard error formula. The issue with means is that the population standard deviation could be anything. And in this case, I'm saying it's often unknown. We actually, in this case, don't know it. So we have our samples, and we could get the sample standard deviation. We did, 4.25. But that doesn't tell us anything with the population standard deviation. The population standard deviation could be any number, and we wouldn't know what it was without actually measuring, doing a census of every car, which is exactly what we haven't done, what we don't want to do, because we want to be able to use inference. So our issue is, with means, and with this particular example, we don't know that sigma. We can estimate it. Basically, instead of using sigma over square root of n, we will use our sample standard deviation over the square root of n. So we do know our sample standard deviation, 4.25. So we can use this in place of this. And we did that last time when instead of using p, we used p hat. So we came up with something that was supposed to be close. However, there's a bigger problem with this. There's a problem when we use this standard error instead of this standard deviation. It's a problem we didn't run into with the proportions. With the proportions, these two things came out almost essentially exactly the same. They were slightly off with proportions, but so tiny that it didn't matter for what we were doing. Here, these are actually off by a measurable amount. So this estimate for this is not horrible, but it causes a new problem. So a problem occurred with this estimation formula. we're trying to use a normal curve, but it sort of caused a problem with the normal curve. The story I'm going to tell you will be of how the person found this, but what the person found was if we had large sample sizes, these two things were pretty close to each other, almost dead on. So this was a good approximation. If the n was small, this thing actually became more inaccurate. It wasn't a very good estimate of this. And it appeared first in this kind of strange example from a guy who worked at a beer factory. So normally we wouldn't talk about alcohol in school, but guess what? We're not in school, so we don't need to worry. All right, so here's the story. This kind of dapper-looking fellow on the left is a man named Gossett. So Gossett was a statistician who worked at a beer factory. He basically worked making stout, and stout is a certain kind of a beer. So Gossett was the one who sort of discovered the problem that I was just talking about and the need for a modified normal curve, which ended up being called a t-distribution. It's sometimes called student's t-distribution. The problem for Gossett is Gossett didn't write under his own name. He, for some reason, used a pseudonym, and his pseudonym was strange. He called himself Student. I don't know why, but instead of writing, when he wrote his papers, instead of going, my name is Gossett, he basically wrote that his name was Student. So you may hear this called student's t-distribution. It's a stupid name, but it's his fault. I don't know why he wrote under the name student, but he did. So this is officially called student's t-distribution, credited to the guy Student, who is really Gossett. But anyway, so we know it's Gossett now. Why he didn't use his own name, I don't know the story that well. But I know this part of the story. So where did the t-distribution come in, and how did he solve the problem of using the sample standard deviation instead of the population standard deviation? Well, here's a story. He was doing hypothesis tests. Basically, what he would do is take the averages for beer chemicals. So, I don't know, say there's supposed to be like 5 ounces of something in the beer. He would want to make sure the beer was good. So instead of, obviously, analyzing all the beer and ruining it, he would take a sample of the beer. If it was supposed to have 5 ounces of something in it, he would measure it in the sample and maybe it would come out as, it's 4.9 ounces. So that would be, within tolerance. But if it came out maybe 3 ounces, it was way too low and it would mean the beer was probably bad. Now, he used sample standard deviations because he didn't know the population standard deviation. So basically he used that formula S over square root of n instead of sigma over square root of n. So he used the S as the estimate. Now he was doing tests, so he did use a 5% alpha level. So basically if the beer was good, remember the alpha level is when you would reject it, he would make a type 1 error 5% of the time is what should have happened. So he was like, if the beer was good, he should have been rejecting good beer 5% of the time. After doing this for a long time, he found out he was actually rejecting good beer 15% of the time. So he was throwing away a lot more good beer than he should have. So think of that, he was making a type 1 error. He should have, basically at 5%, he should have been making a type 1 error 5% of the time. So 5% of the time, he should have been throwing away good beer. Upon closer examination, he discovered he was rejecting the good beer 15% of the time. So there was definitely something wrong. He looked into this, and he must have been kind of a smart guy because he ended up coming up with his own estimates, and they turned out, he wasn't outright a straight-up mathematician, but basically the fixes that he made turned out to be like mathematically accurate. So he was the first one to do this. What he did was he investigated, and he found that the problem was his normal curve that he was using needed modification. He needed to use a slightly different curve because he was using a normal curve, but the normal curve was actually it was not totally wrong, but it was slightly wrong. It was wrong enough to throw this off. So he discovered he was supposed to use not a normal curve, but something that looked very close to it, something that was unimodal and symmetric but had a slightly different shape. This thing that had the slightly different shape, he called a t-distribution. Now, the thing with t-distributions is there's more than one of them. The smaller the sample size, the worse this problem became. So he found out he was using a smaller sample size. That's why he was throwing away so much beer. If he would have upped his sample size, he still would have been throwing away more beer, but it wouldn't have been as bad as this. And if he had lowered his sample size, this would have gotten worse. So we have to talk about this thing called the t-distribution. So this basically reiterates what I said. The estimated distribution that he really needed, the modified normal curve, was basically based on the sample size that he was working with. It became essentially normal with larger samples. So if he took a really large sample of beer, the normal curve wasn't really all that wrong. But with small samples, the thing deviated from the normal curve. So what are these t-distributions and what do they look like? Well, here's an example. The blue curve is normal. He was using that normal curve, but he should have been using the red curve is what he discovered. The red curve is a t-distribution. It's one of many t-distributions. Basically, a t-distribution looks like a normal curve, but the difference is it's a little shorter up here and a little fatter on the ends. Both of these have an area of 1 under them, or it's a probability curve. So they have the same amount of area under them. The thing with the T curve is less of the area is in the middle and more of it is near the ends. So this is why he ran into his problem. If he cut off at like 5%, he was using the blue curve and thought, oh, I'll throw away 5% of the beer. But if you look at the red curve, there's a lot more area under there. That's why he was throwing away 15% of the beer. Basically, this problem occurred because he was using the sample standard deviation and not the population standard deviation. Had he used the population standard deviation, had he known it, he could have used this blue curve. But being that he didn't know it, he needed to use this red curve is what he discovered. That basically the sample standard deviation on small samples had a great amount of error to it. And this curve fixed that error. So if he used the red curve, he was better off. Now, the red curve is only one of many t-distributions. So now I'll show you a picture of a lot of them. If I can get it to come up. There we go. So on this one, the black curve is the normal curve. Now, if he had a very small sample size, so here, if his sample size was 1, his t-distribution was really short in the middle and fat on the ends. If he went up to 2, it got better. It got a little taller and a little thinner on the ends. If he went up to 5, it was taller still and even thinner on the ends. And was getting, as the number went up, as the sample size went up, it got closer and closer and closer to that normal curve. So in fact, as he approached infinity, if you took a infinitely large sample or most of the population, it started to become normal. So really, the trouble was especially bad at the low end if he was taking lower sample sizes, which is what he was doing with the beer. He was trying not to take too much of it because, they wanted to sell it. So the thing with t-distributions is the normal curve is here. There are many, many different t-distributions ranging from short and fat to less short and less fat to matching the normal curve if you make the sample size essentially infinitely large. So our problem is there's all these different t-curves to have to use. The good news is the calculator has all of the t-curves programmed into it in the same manner that it has the normal curve. So basically, in your calculator, there's a t-distribution function for everything the normal distribution would do. So just like there's normal CDF, we'll look in the calculator, we'll see that there's t-CDF. There's also, with inverse norm, there's also inverse t, which we'll use in this lesson. So another technical thing that's important to understand is that to do inference with means, we're probably going to have to use these t-curves. Now, I'll tell you when we do and when we don't. Basically, when in doubt, 99% of the time, we're stuck using these t-curves. There's rare cases where we don't, and I'll explain that in the next slide when we use them, when we don't. There's one more thing that's also a little weird, besides this pad on my laptop going crazy. So the way we define what t-curve we're going to use is based on the quantity n minus 1. So it's not, we don't use the t-curve based on the sample size. We take the sample size and subtract 1. This term n minus 1 is referred to as the degrees of freedom. So this term actually gets used in other statistical things. In fact, we would have used it again near the end of the course, but remember the APs cut that stuff out for the coronavirus stuff. So we're not going to see this term again besides here, but realize if you do take other statistics courses, this n minus 1 quantity appears in other places. So basically doing n minus 1 is called the degrees of freedom. So basically if I had a sample size of 10, I would make a t-curve with what's called 9 degrees of freedom. Or if I had a sample of 50, I would make a t-curve that had 49 degrees of freedom. Or if I had a sample size of 3, I'd make a t-curve with 2 degrees of freedom, and so on. So these things up here were essentially like the degrees of freedom number. Man, this thing won't work. There we go. These are sort of the degrees of freedom number, all right? So that's what we're going to use. So keep in mind on our example, I had 23 cars. When we go to make the t-curve, we're going to use 23 minus 1 or 22 degrees of freedom. So the calculator will make that t-curve for us, and we'll be able to get areas from it and find t-scores instead of z-scores, but it's very, very similar to what we do with the normal curve. So that's what this part says. Once we identify the degrees of freedom, we can use a t-distribution and find a t-score and p-value, and basically we do that exactly like we would have for the normal distribution. On the normal distribution, we find a z-score and a p-value. Basically, if we use a t-distribution, we do the same formula, we just call it a t-score, and we just make sure the calculator uses a t-distribution, a modified normal curve, instead of the regular normal curve. All right, hopefully, I know this is long, hopefully you're still with me. All right, so here's the summary. When do you use the t-curves? You use the t-curves when you don't know the population standard deviation. So this first thing says, say you do know the population standard deviation. Then you don't need to know it, do any of this, right? You can use the normal curve. This rarely happens, but I'm mentioning it because once in a while there's an AP question that's a trick, because we're going to use the t-curve so much for these. There is the rare case where if they give you the population standard deviation, you don't need to do any of this t-curve business. So if you know the population standard deviation, use this formula and use a normal distribution. However, this is like rarely ever happening. In fact, I think even AP, they've only put it on maybe 2 exams in the last decade as a trick question. What do you do the vast majority of the time? Most of the time, we don't know the population standard deviation. So in my example with the cars, I know the standard deviation for my sample. I don't know the population standard deviation. So if I want to do inference to figure out stuff about the real mean, I have to use a t-distribution of n minus 1 or 23 minus 1, which is 22 degrees of freedom. And I will use this for the standard error. The standard error for how far my sample averages can get away from my population average will be estimated by the sample standard deviation over square root of n. So since I don't know the population standard deviation, I'm going to do an estimate with the sample standard deviation, but that's the very thing that causes the problem where I need to modify the normal curve into the t-curve. All right? Remember, there are many t-distributions. Use the one based on n minus 1 degrees of freedom, where n is your sample size. All right. Almost ready to actually build the confidence interval, but we need to talk about conditions because there's a modification to the conditions. Most conditions are the same, except for you see that fourth one. So Independence is still necessary. Randomness is still necessary. So is not grabbing more than 10% of the population. So the first three are the same old conditions we've always tested. Now, the last condition was to make sure we had a large enough sample size. With proportions, that was the success-fail condition. We would do n times p and n times q. Now, we don't have proportions this time, so there is no p and q. So they come up with this new condition called the nearly normal condition. It's based on the sample size. Basically, if your sample size is small, you may run into problems with getting your sampling distribution to be normal or T-shaped. You might notice when I showed you on the last video, when I showed you last year's results for the box, when they were picking out of the box, notice that it, even though it was unimold and symmetric, it came out very boxy. It's because the sample size was small. The sample size was only 10. If it's boxy, it doesn't fit the normal curve super well. If you up the sample size, you get more of those histogram bars, and it gets closer to being a normal curve. So basically, you need a large enough sample size, just like with proportions, you need a large enough sample size to ensure that the normal curve or T curve is a good enough approximation. So in the nearly normal condition, you check the sample size, and you might have to look at the shape of the original data. So there's some cutoffs. If your sample size is less than 15, this isn't the case in our example with the cars, but you could get a really small sample size. So if the n is under 15, you'd have to go and look at the original data. And I'll show you that when we do the example. You have to look at how the original data is distributed. The original data needs to be very closely normally distributed in order for this small sample size to make the sampling distribution a similar shape. If the original data is not, or has some real big skew to it, then the sample size is too small and that normal curve won't really be very good. So for example, that the box example, the sample size was 10. It wasn't quite high enough. And the box data was shaped like a pyramid. So it wasn't normally distributed in the box. The box was like a pyramid distribution. So since it was a pyramid distribution in the original data and the sample size was really small, it wasn't quite good enough that's why it was all boxy, and it didn't quite fit the normal curve really, really well. So there'd be a decent amount of error. So if it's under 15, you want to look at the data, and hopefully you have what's close to normally distributed data. The next condition is if you're between 15 and 40. If you're between 15 and 40, you're usually good to go so long as the original data looks somewhat unimodal and symmetric. It doesn't have to be perfect, just has to be kind of unimodal and symmetric. For our car example, we're in this category. So we have to check the original data. But you'll see that the original data is not perfectly normal, but it has a unimodal symmetric look. If your sample size is sufficiently large, they use a cutoff of 40. Usually after 40, you don't have to worry about what the original data looks like. The original data could look like anything. It could be super skewed. It could be uniform, whatever. That central limit theorem kicks in. As you increase the sample size, you get a better and better and better histogram that looks like a normal or T curve. All right. So if the n is greater than 40, that central limit theorem kicks in, and most of the time you don't have to worry about checking anything unless, you suspect that the data is really, 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 really bad. And then the higher this number gets, the less this even matters. So if you're kind of close to that 40 or 50, you want to make sure your data isn't too bizarre. But if your n is like 500 or 1,000, then this won't even really matter anyway. All right, so this nearly normal condition, basically when you write it, you just note your sample size. If your sample size is under 15, you got to look at the original data. If your sample size is between 15 and 40, you still want to look at the original data, but it just has to have a roughly unimodal and symmetric look. It doesn't have to look really normal. If you're over 40, you usually don't have to check anything. You can just go ahead. So in our case, I'm going to have to do this part. Finally, building the confidence interval. Good news is the structure of the confidence interval is the same as the proportions. Basically, you use your sample mean before we used our sample proportion. Now we use our sample mean, and we do plus or minus. Oh, my minus is missing. Let's see if I can add it in. I should have put that in before I started recording the video. Let's put it in there. There we go. It's plus or minus. All right. So when the conditions are met, we build the confidence interval by using our sample mean plus or minus. Now, this used to be z star. Since we're using a t-curve of n minus 1 degrees of freedom, this is how we represent that. So we're not finding a z-score. We're technically finding a t-score. It's basically the same thing. It tells us how far to go out, and we need the standard error. So the standard error is that formula s over square root of n, or sigma over square root of n if you happen to know sigma. If we build this, this will be based on the confidence interval or confidence level. Basically, we'll be C% confident the real mean is in this interval. Remember, C we choose. Typically, we would do 90, 95, or 99, but you can choose any kind of number you want. Typically, no one does it under 90 because there's no point. Most confidence intervals are 90 or greater, all right? So we've had this structure before, a point estimate plus or minus t or z score times the standard error. So it's the same formula, just with a mean plugged in and with the t-score instead of the z-score. So finally, let's create a 90% confidence interval for the average speed of cars by the school. So basically, the reminder is the mean of cars was 31.04 miles per hour. The standard deviation for that sample was 4.25. How can we use that to know a confidence interval for what the population's average might be? All right, so that's what I'm going to show. So time for the board behind. So I wrote up top our mean 31.04 of our sample. Our S, the standard deviation of our sample, is 4.25. We don't know mu, we don't know the population average, and we don't know the population standard deviation. Before I go to do the confidence interval, I do want to check conditions. We always check conditions, whether it's a test or a confidence interval. So make sure on your AP exam, always check the conditions before you do a procedure. So the check is, check if it's independent. I mentioned, in general, it should be. One car's speed shouldn't affect another. Now, we would have to be careful. If traffic is heavy traffic might affect the car's speed. If I want to speed, yet the person in front of me is going slow, I have no choice but to go slow. So long as there isn't too much traffic out there. Now, I'm assuming, we'll just, like I said, assume it's Reynolds Road outside the school. That road's never outside the school overly busy. I've never seen that backed up or anything. I mean, there's a traffic light there, but pretend we did it away from the traffic light. There's usually not enough out there. So I'm going to assume that one car is not affecting another. Just be careful. Obviously, if it was like Manhattan with heavy traffic, that wouldn't be true. As far as randomness, once again, they normally would tell you that it was randomly done. We'll just trust the people who did the study. I think it did say something that they were randomly picked anyway. The 10% conditions met. 23 is definitely less than 10% of all cars that drive by the school. There's probably hundreds that drive by each day, probably thousands a month, whatever. So 23 is definitely less than 10%. And now the nearly normal condition. Our 23 is less than 40. It's bigger than 15, but less than 40. So we do have to check to see if the original data is roughly unimole and symmetric. I'm going to use the calculator to make a histogram of it. So basically, I entered into the list. So I'll show you my list. I entered, I don't know why you can see this, but I entered in all the data. So all 23 data points are in list 1. You can go to stat plot. I turned my stat plot on, and within there you can make a histogram. So I turn the stat plot on, and then under where it says type, notice I highlighted the third option. See if I can get my finger to point at it. I highlighted that third option. That option is to make a histogram. So I turn the stat plot on. I want to make a histogram. And I want to make a histogram of list 1. That's where I stored my data. So it'll give me a histogram of how spread out those like a histogram of basically the speeds. So next you go to zoom stat. Remember that's zoom number 9. And if you do that, it'll make the histogram for you. So this is a histogram of the original data. Notice the original data. This is the speeds of the cars going by. It's roughly unimodal and symmetric. It isn't perfect. It doesn't have to be perfect. We're between 15 and 40. We're just looking for roughly unimodal and symmetric. It's sort of high in the middle, low on the ends, good enough. So long as it's close, even if it's not all that close, as long as it looks roughly that way, we're good. So basically, the nearly normal condition is met. The original data is roughly unimodal and symmetric. Our sample size isn't super big, but it's, in this case, we don't have to worry about the t-curve or the normal curve not being appropriate. So basically, our sample size is large enough with this data for the central limit theorem to kick in, and basically we can use a z, or a normal or t distribution. We'll use a t distribution because we don't have the population standard deviation. Finally, let's make the confidence interval. So since the conditions are met, I always forget to put this on here. You should put the bottom, since the conditions are met, I'm going to do a one sample t interval. All right, so here's the formula for the confidence interval. I need a decent amount of information, so I put the information on the side. Remember, x bar was our average speed of cars. Our standard deviation was how much those were spread out. So I got those in the calculator by doing one variable stat on that list in the warm-up. These are our sample numbers. I also have my sample size. There were 23 cars in my sample. That lets me get the degrees of freedom. The degrees of freedom is 23 minus 1, which is 22. So when I make the t-curve in the calculator, I'll show you how to get that t-score that I have over there. So I'm going to use 22 degrees of freedom. Standard error, I don't have the population standard deviation, so I have to use the sample standard deviation over the square root of n. The sample standard deviation is 4.25, and use the 23 for this. N minus 1 is for the degrees of freedom. Use the 23 here in the formula. 4.25 over square root of 23 comes out as 0.8862. So this is how much I expect the sample to deviate from the population, even though I don't really know what the population is, population speed number. All right, so this lets me plug some stuff into the confidence interval. X bar is X bar. The standard error for X bar is this calculation. The last thing is getting the t-score. Now, the t-star, notice I put 22 under it. That symbolizes that I'm going to use a t-curve with 22 degrees of freedom. Now, how do I get the t-star? If this were a normal curve, we know the number for 90%. The number for 90% was 1.64. But we can't use that number because the t-curve is a little shorter and a little fatter. So the cutoff for 90% is in a different spot. So that trick I showed you of how to find a z-score for any confidence level, you need to always do it for the t value. So basically, that's what I have down here. Since we desire 90% confidence, I need to figure out what t-score covers 90% of the t-curve. We'll start with 0.9. That's what 90% is. Remember, cut that in half. Make it 0.45, then add 0.5 to it. It makes the number 0.95. Now, if we were doing a z-score, we would have did inverse norm of 0.95. Since we're doing a t-score, we're using a t-curve, which is a little shorter and a little fatter, we need to put two things in the calculator. We need to put in this number that we calculated, basically cut the confidence level in half and add 0.5. We put that in the calculator, but we have to also tell the calculator what t-curve to use. We want to use a t-curve with 22 degrees of freedom. So the way you do that is you can go to second distribution. I'll try to get you to see it. And you'll notice that there is an inverse t option. I want to go down to inverse t. So I'm going to inverse t and selecting it. You want to enter, since I want 90% confidence, remember, don't put 9.90 in there. Put that number I calculated, the 0.95. So I want to know what's the t-score that will get me out to 95% of the curve on either side. But it needs to be a t-curve of 22 degrees of freedom. So where it says df, you put in the degrees of freedom. So now I'm going to figure out what that is. If you have an old calculator, you would enter it like this. You would enter the area first and then the degrees of freedom in the second slot with a comma between them. And now it gives me the t-score. So if it were a normal curve, we would go out 1.64 standard deviations. But the t-curve's a little shorter and a little fatter. We need to go out further to get to 95%. We need to go out to 1.717 standard deviations. So that's where this number's coming from in the formula. All right. So this section gives me the t-score. This information gave me the rest. All right. So finally, what is the confidence interval? Well, with this calculation now ready to go, I'm doing the 31.04 plus or minus that t-score 1.717. That'll take me out 90%. And times that standard error of 0.8862. The confidence interval, which I've been looking at for a while now, is 29.52 to 32.56. So this is a 90% confidence interval for the true population mean for the speed of the cars that pass by the school. So our sample came out 31.04, but we're 90% confident the true mean of all cars that pass by the school, their true mean speed is anywhere from 29.52 to 32.56. What does this mean for our question? Well, remember, the parents were worried about are people speeding. This confidence interval says that maybe they are, maybe they're not. We're not really that concerned because it's possible the real mean could be 29.52 or 29.8. That's the case, they're not speeding. Now, it is also possible it's 32 miles an hour, which means they are speeding. So this confidence interval seems to support the fact that it's possible the population isn't speeding. Now, if the confidence interval were 35 to 40, then we would be 90% confident that they were actually speeding. So remember what 90% confidence means. It means that 90% of the time when we take a sample of this size, this procedure will capture the real value. So once again, we have a 10% chance here. Well, there's a 10% chance this procedure won't capture the real value. I shouldn't say there's a 10% chance this has or doesn't have it. This either has the real value or it doesn't. The problem is we don't know. So it doesn't have a chance. It either has it or doesn't. We just know this procedure generates a confidence interval with the proper number in it 90% of the time. So hopefully this is one of those times we capture it. So that's why we're 90% confident. So once again, 90% confident the real speed of the population that goes by the school on Reynolds Road, for example, is 29.52 to 32.56. The last thing I'll mention, because this is probably my longest video. I mean, this would have taken several days in class, so hopefully you're still with me. But the last thing I will mention, and I promise it's over, is that the difference between statistically significant and actually meaningful. In this case, even if the real value, say the confidence interval came out 31 to 33, say those were the real numbers. Oh, people are really going 33. Even though that would be statistically significant, they would definitely be speeding if the confidence interval was from 31 to 33. It wouldn't be very meaningful, right? Like, are people going to, are kids going to die because they're going 2 miles an hour over the speed limit? Is it good they're going over the speed limit? No, but they're not going over the speed limit in a manner that anyone would care about. Now, if the confidence interval were 40 to 45, then you'd be like, oh my goodness, the real speed's 40 to 45. That is significantly faster than the speed limit, and that is something that some kid crossing the road, could get hit by somebody who's speeding. So that would be a case where you might want to get a cop out there or a speed bump or something to slow people down. So in this case, our confidence interval doesn't even support the fact that they're necessarily speeding. But we'd also have to be careful if that confidence interval was 30.5 to 32.5. It would be statistically significant, but it wouldn't be worth actually doing anything about, right? You're not going to go and do crazy things to Reynolds Road for a 1 mile an hour over the speed limit difference. So make sure you know the difference between statistically significant and actually important. In this case, the result is neither, because we don't even have evidence that they're speeding. And even if it is the 32.56, the worst case scenario, that's not enough to really do anything about. Okay? So this is how you make a one sample t interval for the mean. So this is how you can make a confidence interval for the real mean given a sample mean. All right? And may put up another example of this because I know this video was long. It had a lot of the theory in it and technical stuff. So I will put the assignment up with this, but I may decide to do a subsequent example if it becomes necessary. So you can let me know how the homework goes and if you'd like to see another example or not. All right? Well, I will finally end this. Have a good day or night whenever you're watching this.